obviously the guys who aren't here will get to be able to watch it back as well. So we're having issues last week with people not being able to see the any of the videos or anything. So for that, you just need to double check that you haven't accidentally spotlighted yourself. Because if you spotlighted yourself, then that's all you'll see.
So that way you guys can watch it back
So
in case
please
you missed anything.
double check that
And
you've
obviously the guys
not
who
done that.
aren't here will get to be able to watch that back as well. So we're having issues.
And just using two computers, so the other one's making sound, so I'm going to mute it. Okay, so first thing we're going to talk about is, so this week's topic is all about faults. So so the objective tonight is to understand the common types of electrical faults, symptoms and causes, identify dangers and consequences associated with those faults, and just an introductory understanding of the solar and their components and the dangers associated with solar installations and how to mitigate them. So a bit of revision first. Cool. So when we looked at circuit wiring and all the block course things last week, cool. So in New Zealand, how do we wire our socket outlets? Series or parallel?
Say it.
Parallel.
Yeah, we wire pretty much everything in parallel. The reason we do this is because in parallel circuits, like we talked about last year, voltage remains current. And if we were to wire things in series, we would have incorrect voltage. Have any of you guys seen what happens when you get under voltage with appliances? Yep, they break. Sometimes they break, sometimes they'll still try to run. So, for example, a motor, if it's got under voltage, it'll still try to run, but it'll be drawing so much current through the windings and through the cabling that they'll heat up, and then eventually burn out if the thermal overload doesn't engage. Or some electronic components will fail and rupture as well. So the one time I had a call out one time for a customer was complaining about not the lights flickering. He couldn't use his appliances. The transformer had gone faulty on the street, and so he only had about 130 volts at the outlet and at the switchboard. So it is common. It is not overly common, but it is possible. Cool. So are there any other way? What are the different ways to wire a two-way lighting circuit? Yeah, so there's two ways to do it. So you can connect. Yeah, so there's running this. So you run the strap cable. You always run the strap cable. You don't do the old school way where they. I don't know if I can share a photo to you guys. Oh, okay, never mind. So I did one job over the Christmas break where they had run two core and earth. Yeah, multiple cables. Yeah. So they ran two core and earth as a strap, and then they sleeved the earth and neutral with blue heat shrink. And that's the way they did the old school two-way. So the two ways you can do it, so you can run the strap, you connect the light with the red of the strap wire and connect the feed to the common on its own. This requires one extra connector than the other method, which is you put basically white with the light and blue with the feed and red in common. So you take the white and the control for the light, put them together. You put the feed with the blue, and then you put the red from the strap wire into the common, which requires one less connector. Which, if you think about it, if you're doing say 100 units in a apartment building, and they've each got two or three two-way or intermediate circuits, those connectors. So that's what, 3 or 4 jars of connectors. So it does add up materials cost wise eventually. Most of the time it's all good. So, does anyone remember how a 3 heat switch alters the heat levels of a load? I like the honesty. So, the basic way it works is it changes the configuration between. So there's a 3 heat switch. So a 3 heat switch for a heater, basically there's two elements, and the 3 heat switch switches between the two elements being in series with each other. So they put out less heat on the low setting. On the medium setting, only one element turns on. And then in the third heat setting, it puts them into parallel. So it switches the elements between series and parallel. So it alters the voltage applied to the loads and the current. And so it changes the overall power that's converted into electrical heat. And when you guys are on block course, you guys will get to play around with the 3 heat switch to see how it works. So either us here or someone out in the other regions will take you through how to wire it, how it works, and you'll get to use a couple of light bulbs to simulate how that works. Cool. How do you change the rotation of a 3-phase motor? Yeah, so 3-phase motor is the easiest to change direction because you're just flipping two of the phases around. And you can do this um, either at the terminal box. If you're going to do it permanently, you can do it manually, or you can set it up so you've got two contactors that flip the phases going to the motor. How do you change the direction on a single phase motor?
Swap one of the two windings, so either the start or the run winding, the connections for just one of them.
So yeah, swapping the start or run winding so by swapping one of the windings around, you're reversing the polarity. It's usually done with the start winding. If it's a motor that drops the start winding out, this is so a cap start motor, you'd normally do this, but if it's a cap start, cap run, where both windings are used continuously, it doesn't matter which ones you swap around. But usually it's done on the start winding. Cool. So now we're going to talk about the different types of faults. Yeah, the motor does need to stop before you make it spin the other way. You could try, and some of the guys have accidentally done it here in the workshop, where they wired up a Ford reverse starter motor and they tried to make it spin the other way before it had stopped, and the motor was not very happy. Thankfully, we don't use expensive motors here in the workshop, relatively speaking, but they are still pricey. So this works. Cool. So in the link in the chat, I have posted a Google Drive link for you guys to download. It is a faults table handout. So it's basically what we're covering tonight. Let me know if anyone can't access it. I remembered to change the permissions this time so that anyone who had the link could access it. So I don't have to verify you individually. Cool. So there's all kinds of faults in the electrical industry. So what kind of experience have you guys had with fault finding? I know some of you guys do service work. Like what is the most common type of fault you come across? Just the basics of it. Is it like an open circuit, short circuit, something's broken, overcurrent, overload? Yeah, there's all kinds of faults out there. So I think the strangest one I've ever attended was a two-story unit. So it was split top and bottom. And for some reason, they'd run the mains cable in between the units, so through the ceiling of one and through the floor of the other. And when they'd replace the flooring or carpet upstairs, for some reason, they'd used nails that were too long. And so they'd shot the nail straight down through the floor and into the mains cable for the unit down below. And so the pole fuse just kept blowing. And because they wouldn't let us open up the ceiling, we had to run a new mains cable and conduit around the perimeter of the outside of the building. So mains came in the top on one side, went down through the floor/ceiling, and then into the meter box. So the meter box was on the complete opposite side of the house to where the mains entry was. Because, Sparkies back in the day were amazing. Cool. So you've got that list. So some of the faults you normally come across. So open circuit. So the definition of an open circuit is a discontinuity in the circuit. So basically, it's a break in the circuit. Oh yeah, that does happen. Yeah, if they share any type of phase or neutral, that's a good one. The other one is when the neutral breaks and all the power is flowing through the earth stake. I've heard guys talking about if the earth stake's got enough fault current running through it and the ground's wet enough, the ground will actually boil. Um, None of them have shown me a video, but they've told me it happens. So if I ever see it, I'll be sure to get a video. Yeah, so basically it's a break in the circuit. Just prevents current flow, so it's just a clean break. Um, so just basically you'll have things that are not working. You'll have a volt drop across the open section. So yeah, consequences is basically stuff doesn't work, but it does mean there's a potential live dead end somewhere for someone to come across, or maybe it arcs across near some insulation that catches fire. So you've got short circuits, so direct connection between two conductors bypassing the load. So this is where like your mouse is chewed through the cable and has touched phase to earth and it's created a dead short. So it's sudden tripping of breakers, sparks, it's potential for overheating and fire. And the consequences are like higher fire risk, damage to cables and connected equipment. So earth leakage fault. What do you guys think is the most common form of earth leakage?
One that I think of a lot, especially with the industry I'm in, is moisture getting into things, especially like ovens and that.
Yeah, moisture is a good one. In my experience, the most common ones I've come across has usually been from appliances. So appliances that have got a slow leak from either neutral or phase to the frame of the appliance. So that's where, like, usually it's the El Cheapo microwaves, kettles, usually kitchen appliances, the cheap ones. So the amount of state housing call outs I would get for RCD tripping, the people would be like, "I just bought a secondhand microwave or a secondhand kettle." You plug it into the socket outlet, turn it on, trips. Test the socket, RCD is working perfectly fine. Sorry, unfortunately, you need to buy another kettle or another microwave or toaster. It's the usual culprit, and 9 times out of 10, yep, freezers, yeah, freezers because the compressor as well. Same with fridges. But yeah, the amount of times I've ended up taking appliances away for people who are like, I don't want to accidentally use it, so I've ended up with crap ton of broken microwaves and kettles to throw in skip bins whenever I find them. So the definition is basically current leaks to the earth instead of returning via the neutral. So the RCD trips, it's risk of electric shock when touching appliances or exposed metal. So if you've got a kitchen bench and for some reason the appliance has got an earth leak and it's leaking to the stainless steel bench, you can get a shock from that. Although it is technically still a requirement that we bond all extraneous metal fittings. So stainless steel bench should be bonded anyway. So basically the consequences are electric shock, equipment malfunction. Oh God, bless her heart. Yeah. I don't know if anyone else has done this, but I got requested to do a job over the Christmas break. They wanted a PowerPoint on the soffit of the house so they could run Christmas lights over Christmas time. I don't know if anyone else has had to do a job installing those, but apparently they're very common over in the United States. They call them holiday receptacles because they're only used for Christmas lights. So then we move into overcurrent or overload. So it's where current exceeds the safe operational limits of a conductor or device. Um, Possible symptoms: overheated cables, melting insulation, equipment damage, and there's just risk of fire, component failure, and reduction in system reliability. So have you guys looked closely at the circuit breakers that we use? They'll have the C6, C16, or C20 rating, but they also usually have a rating for that's in KA, anywhere from 4.5 to 6 to 10. Do you guys know what that means? Yes, Daniel. Yeah, it's in relation to VSCC. Yeah, yeah. So basically, that's the so C16 is the current that it's meant to trip at within 4 seconds at 5 times, but the 4.5 or 6 KA rating or 10 is the maximum current it can withstand before it will break or deteriorate or may not trip at all. So when you do your PSC on the mains and you get a reading of say 3 KA, you know that a 4.5 KA breaker is more than fine to be in that installation because the maximum short circuit current is less than 4.5. But obviously, depending on how close you are to the transformer or the substation, sometimes you can get up to, I think the largest I've had is 8 KA from a house that was right next to the transformer just on the other side of the Haywoods. So we had to put 10 KA breakers, which was slightly more expensive. And those rewirable fuses that we aren't allowed to install anymore, but are still around, those are considered to be rated at 1 kA, so only able to stand 1000 amps before they may not correctly disconnect the circuit. So yeah, that's why one of the main reasons why we don't do it. Yep, super safe, just like Super 6 roof. I'm hoping you guys know. So Super 6 roof is the corrugated asbestos roofing material that they used back in the day. Yeah, loose connections. This is really common in new builds. The amount of times I've checked over some of the guys' work that I've been working with when I've been doing testing, and I'd find like weird, getting a weird phase reading, pull the socket off, and they've barely tightened the screw down. Or you, when I go and test some of the switchboards in the training center here, but one of the tests we do is we yank on the cables that are going into your circuit breakers, and if we pull them out, then you have to redo it. If the guys who are coming from overseas do that, we basically say you've got one more chance. If you do that again, fail, you're not getting qualified. We're not going to deem you competent. So yeah, partially connected or improperly tightened conductor leading to intermittent contact. So you'll get things like flickering lights, intermittent operation, excessive heat, voltage drop. So the consequences are overheating, fire hazard, reduced equipment lifespan. So it'll affect the lifespan of the equipment you've installed. Arc faults. So has anyone here installed arc fault breakers other than me? So they're not cheap, but they are quite an interesting piece of equipment because they detect the frequency at which the current's flowing. Oh, Jordan, you've installed some? That's cool. So yeah, they're actually got a circuit board inside them that detect frequencies that they know are the changes in the frequency, so they know what an arc is, and they're actually programmable. So they're very kind of hush hush about the way they're doing things. One of the tutors we've got here used to work for Hager as one of their sales reps. And so he knows quite a bit about the stuff going on in the background. But obviously, you can't tell us too much because of non disclosures and lawsuits. So it's unintended electrical discharge between conductors due to damage, insulation, or loose connections. So it could be that you've got, a break in a cable that's maybe 1 or 2 millimeters and it's just arcing across. It's not quite broken enough to not not lose connection via that arc. So the arc fault breaker will detect that and trip, but a normal circuit breaker may not detect it. So the risk of fire is quite high. So yeah, you'll hear crackling or buzzing sounds, you'll burnt smell, scorched material. Sometimes when you pull a socket off the wall and you kind of see it arcing as you pull it off, that's always fun. So your consequences, it's high fire risk due to the sustained arcs. And you've got, like we're talking about before, under or over voltage. So supply voltage deviates significantly from the nominal range. There is actually a requirement in the legislation about the point of supply. So you're only allowed to, I think some of the network guys might know more off the top of the head, maybe. There's actually a plus or minus like a percentage of volt drop that is allowable before it gets to the house or point of supply. So under voltage, you'll get dim lighting, motor failing, or decreased motor torque. 4%. Yeah, that sounds about right. And over voltage, you'll get bulbs burning out and overheating. So it's potential damage to sensitive electronics. Also for the smaller single phase motors, there's a chance that the over voltage will burn out the windings. One of the ones that is installed at a property in Willa Street in town, they lost 2 motors to burnt out windings because we reckon it was because it was the day after we had thunderstorms. There was probably over voltage due to the lightning in the transmission lines, and they didn't have any surge protection on the building. So we couldn't find any other reason for it other than over voltage burning out the windings. So yeah, they had to replace the two, was it $75 motors that they installed? But there are also inbuilt in certain places where they employ monitoring to detect under and over voltage, and then it cuts the supply, or it uses capacitors or surge protectors to protect the installation. Cool. Insulation failure. So it's pretty straightforward. Degradation or damage to a conductor's insulating material. So you've got a lot of old wiring in New Zealand, particularly. Do you guys know what VIR or vulcanized Indian rubber? It's a kind of a black rubbery cable. You see it a lot in old homes. It's actually, there's a whole bunch of it in a house that I am looking at trying to buy. And everyone else is scared of it, but obviously me being a Sparky, I'm like, yeah, no big deal. Just take me a couple of days to sort it out. Oh, the old metal conduit too. Yeah, yeah, I've seen a bit of that. We had to rewire a house in Karori that had that stuff in it. The boss originally wanted us to just pull wires through the conduit. We tried for, yeah, unless you've got a saber saw, then it's real quick. Saber saw or a grinder. Yeah, it's just increased risk of earth faults because of the lack of insulation. So you're going to expose live wires and shock hazards, and the consequence, electrical shock and equipment damage. Along with that conduit, the old metal, you got to remember when you're doing work on that stuff that conduit is technically the earth. That's how they got the earth to the power points. They just ran red and black cables in the conduit and had the conduit as the earth, which is also kind of what they do in America as well. Yeah, Americans. Nope. So high impedance faults. So when we talk about impedance is what we talk about with AC resistance. So when we looked at resistance last term, it was all in DC circuits. So when we talk about total resistance, it is DC. But when we talk about AC, there are other things that have factors in AC, such as inductance, capacitance, and all that. And we call that the total impedance. So the impedance is the total opposition to current flow within a AC circuit. So that's the difference between what impedance is and compared to resistance. So the most time you guys will deal with impedance day to day is when you do your earth fault loop. Who can tell me the route that your fault loop impedance tester takes? So it tests from where? I'll tell you, it starts at the earth pin on the socket outlet, and then it comes back to the phase. But what's the pathway? Yep, it does go back to the transformer. Yep. And so the route it takes is it goes from the earth pin of the power outlet back to the earth bar, through the MEN link to the neutral bar, down the neutral, back to the transformer, back through the phase, and to the socket outlet again. So it goes all the way back to the transformer and then to the furthest back MEN point where the neutral is connected to the phase. Yeah, it actually doesn't go through the earth. It actually measures the neutral, because the neutral back to the transformer is a lower resistance path than the earth itself. The earth is just there to make sure that the breaker trips in the event of an earth fault, but it actually goes down the neutral to the transformer, back through the phase, through the main switch, through the breaker, through the RCDs to your socket outlet. So that's the earth fault loop path. So that's your meter is measuring that entire way. It depends on your tester. Some testers it will test it in about 2 seconds. Mine takes about 5 seconds, 5 to 10 seconds, because it's a bit older. So it doesn't take very long, but it depends on how good your meter is, because your meter is also putting quite a bit of current through that to get it to do it. But yeah, so that's what gives you your prospective fault current and lets you know if the breaker is going to trip or if the breaker is going to fail because the current's going to be too high. So yeah, so when we talk about high impedance faults, so it's normally a high resistance path to earth or another conductor. Normally it's due to a poor connection at a socket outlet. So if you do an earth fault loop test at one socket outlet in the circuit and it's good, and then you go to the next one and it's bad, there's a bad termination at either of those socket outlets or one of the ones in between. So you get a subtle performance reduction, often undetected by overcurrent devices, and it's prolonged overheating and insulation damage. So that high impedance join will become a hot spot and eventually heat up, and then possibly break or melt. And my favorite one, polarity transposition. So by definition, it's an active phase neutral earth conductor that's been incorrectly connected. So the symptoms: unexpected appliance behavior, risk of electrical shock when off, and equipment damage or severe shock hazards. One of the best ones I've heard about was an American. Yeah, yeah. There was an American in Island Bay who rewired his house. And because in America they're used to using black as the live wire and white as the neutral, for some reason he assumed we used red here as the neutral. So he wired all of the lights in the house with neutral switched. So all of the connections at the lights were live all the time because he was switching the neutral, which outside of specialized equipment you should never do. And if you do, you have to switch the active first before the neutral disconnects, and then when you reconnect it, the neutral has to connect first. So when you have those bypass switches for generators, they disconnect the neutral, then they disconnect the phase, then the neutral, and when they reconnect the neutral, then the phase. It's a special type of switch. Cool. So now, hoping this works, we're going to look at. Okay. I'm sharing a PowerPoint. Can anyone not see it? Should have a thing on the screen that says electric faults. So Thomas, double check that you haven't spotlighted yourself. Okay, can everyone see the screen now? Okay, Case, check that you haven't got yourself spotlighted. We've tested it as many times as we can with other scenarios. I'm not sure what the problem could be, but just double check you haven't spotlighted yourself. So, cool. So, electrical faults. So we're just going to go through some common electrical faults in the industry. So basically, what's going to happen is you're going to get a customer's going to give you a description of what's going on, and then I want you guys to tell me what the fault is. So first one, hi, I've been having issues with the power in my home office. Whenever I plug in multiple devices like my computer, heater, and printer, the power cuts out and the circuit breaker trips. It doesn't happen when I use just one or two devices, so I think it might be an issue with the amount of power being used. Can you help me figure out what's going wrong and how to fix it? Okay, most of you, yeah, got it. So basically, it's an overload fault. Tim. God. Yeah. So basically, they're using too many appliances. They need to either, yeah, you need to either run a new circuit to the office or they need to, yeah, not use as many. I think personally, if I had a home office, I'd be running two circuits at least. Cool, next one. Hi, I need some help with the light in my living room. It suddenly stopped working yesterday, even though it was fine the night before. I replaced the bulb to see if that was the problem, but it still doesn't turn on. I've checked the plug and switch, and everything seemed to be connected properly. Can you let me know what might be going on and how to fix it? Cool. So it is an open circuit fault. So basically, there's a break in the circuit somewhere. Light fittings, they get old, they deteriorate, especially one of the things with bayonet and Edison screw light fittings is that it's very easy to just chuck in a bulb that's too strong because those fittings are actually rated to a certain wattage before the like it'll melt the fitting. I've seen times where the fittings have melted because they've put one of those heat lamps into an Edison screw socket. Yeah, some people have no idea. Cool. Hi, I'm having a strange issue with an outlet in my kitchen. Whenever I plug in my kettle and turn it on, there's a quick spark at the outlet and the circuit breaker trips immediately. I tried using the kettle in another outlet and it works fine. So I'm thinking it's something to do with that specific outlet. Can you help me figure out what's going on? So yeah, it's a short circuit fault. It could also be, yeah, there could be water in the outlet. It could be a loose connection. Yeah, generally I would think it's a loose connection, but obviously you'd open up the outlet and just have a look. Hi, I've noticed something odd with one of my power outlets. When I plug in my heater, the plug gets really hot after a while, and I've even seen some scorch marks around the outlet. The heater seems to work fine, but I'm worried there might be something wrong with the outlet itself. Can you let me know what might be causing this and if it's safe to keep using it? it is a loose connection fault. Just because the way to tell that is the scorch marks and the heat. That's where you get the loose connection causes that heat and the scorch mark. I think there's a problem with the wiring in my dining room. I've been hearing a buzzing sound coming from the light switch when I turn the lights on. Yesterday, I also noticed a faint burning smell in the room, but I couldn't find anything obvious. The lights still work, but I'm worried it might be something serious. Can you take a look and let me know what's going on? Cool. So it's an arcing fault. Yeah. So yeah, that crackling is what you get when there's a loose connection or an arc or a burning smell. So it's either going to be a loose connection or it's going to be arcing. Either way, you're going to open the light switch and see what's going on. Hi, I've been having an issue in my living room whenever I use my portable heater. Every time I turn it on, the lights in the room get noticeably dimmer. The heater works fine, but it seems like it's affecting the lighting somehow. This hasn't happened before, and I'm wondering if there's a problem with the wiring in the circuit. Can you help figure this out? So the clue is the fact that it's heater and lighting. Yeah, so it is most likely under voltage. And this is usually going to be caused by a loose neutral connection. So if you have a job where they complain that when they turn the stove on or they turn the heater on, the lights start to flicker and go dim, that's usually a sign of a loose neutral connection or a broken neutral. And so all of the current is then flowing through the earth, which isn't as good a conductor as the neutral. So yeah, that's one of the best signs that either there's a undervoltage problem, broken neutral, might be that the phase connection at the pole isn't as good. I've had that a couple times as well, although the linesman never wanted to admit that I might be right. Cool. Hi, and 7. You check the supply voltage at the you check the supply voltage at the main switchboard. You'd turn the power off, disconnect the MEN link, turn the power on, and see what kind of voltage you have between phase and earth and phase and neutral. If you're getting 230 between phase and earth, but only say 210 or 200 between phase and neutral, it means there's an issue with the supply neutral. The main reason I think it's the main neutral with that one is because it's when the heater's turned on, the lights flicker, because those are on two different circuits, because the lights are on one circuit and the power points are on another. So it makes me think that it's all the way back at the mains rather than just at the socket or at the light switch. Yeah, the next one at 7. Hi, I think I might have a problem with the wiring in my attic. Recently, I've noticed flickering lights in one of the upstairs rooms, and when I went to check the attic, I found some chewed up wires. It looks like the insulation is damaged and the metal inside is exposed. I'm not sure how serious this is, but I'm worried it might cause a bigger problem. Can you advise on what to do? Yeah, well, usually, yeah, if the client's telling you they've seen exposed wiring, it's like, well, cool, there's an insulation breakdown. They've kind of solved the fault finding part for you. But yeah, just because the symptoms are one thing doesn't necessarily always mean it's that. Sometimes I've had the description from the client and thought it's one fault, and only 10, well, depending on the size of the house, it might be more than that. Yeah, so the client's indicated one thing, and then I thought it's one fault, gone to fix it, and found that actually it's this, and I was completely wrong. Um, but sometimes you just gotta. So yeah, it's an insulation damage fault because there's just the client's seen insulation damage. Cool. Hi, I've been having a strange issue with one of my kitchen appliances. I got a small shock when I touched the metal casing, even though the appliance was turned off at the switch. Doesn't happen with any of the other appliances plugged into the same outlet. I'm really concerned because it feels dangerous. Can you let me know what might be causing this? So it is a polarity fault. Bit of a tricky one because the basically if the switch is off, the power should be off. So the switch at the wall socket, but because someone's got the yeah, well, it depends on what the floor material is. Because if you've got decent, like if you've got vinyl, which is fairly well insulated, and you've got shoes on, then you're only going to get a small zap off an appliance with a polarity issue. So yeah, it's a probably most likely that they've got the phase and the earth around the wrong way. Um, yeah. So unless you're touching the stainless steel bench and holding onto the appliance at the same time, you're probably just going to get a zap. I mean, I've been zapped a few times by PowerPoint circuits, and yeah, it's a zap, and then you get like your hand gets thrown back because it's AC. But yeah, it's a polarity. Yeah, it's a polarity fault. It could also have been earth leakage. It's very possible, but in this case, it was a polarity fault. Well, hi, I'm having problems with one of my appliances. Every time I turn it on, the power cuts out and the safety switch, RCD, trips. I've tried using a different outlet, but the same thing happens. Other appliances work fine in the same outlet, so it seems to be an issue with this specific appliance. Can you figure out what's going on? You guys go for the Timo. Oh, I love it. Okay, so it is a earth leakage fault. It's a problem with the appliance, which is what I would find when I was talking about those cheap appliances that I would find. And there must be a DeWalt. Yeah, I've seen they started selling DeWalt car chargers now at Bunnings. I'm very scared about those things. But yeah, there's a saying we use here in the trading center. Oh, must be made of Chinesium, the strongest material known to man. So yeah, anything made in China is made out of Chinesium. Cool. So now we're going to take a look at solar power system components. So I don't know if anyone here does solar. It's very specialized. But yeah, the different components that are in a solar install. So you've got your solar panels. So this is what sits on the roof, or if it's a ground mounted system on a kind of a stand that's above head height. So you got your panels, your racking, your mounts, and clips. And each panel should also have an earthing clip as well. And go back. And so you've also got your other components. So you got your PV panels, so they're usually installed on the rooftop or ground mounted frames. The efficiency depends on sunlight exposure, angle, and the panel quality. And then from your panels, you go down to the DC isolator. DC isolators they have switches that are wider. So if you look at the distance between normal normal isolator, AC isolator, the gap between the switch contacts will be closer together than a DC isolator, just because of the potential for arcing on the DC side. Then you've got your DC to AC inverter. You've got an AC isolator, and then that feeds back to your switchboard. Yeah, so the inverter converts DC to PV from the PV panels to AC, which is used by the appliances in the electrical grid. So you got string inverters, which handle multiple panels connected in series, which is shown here. And you've got micro inverters. So each panel gets its own inverter for higher fault tolerance and efficiency. So instead of having an inverter down mounted inside the house, you have a inverter for every panel. Hey Levi, all good. Everything's being recorded, so it'll be up on YouTube later. I'll be sure to give you guys the name of the channel to look up after we're done. So cables, so you got the cables, they carry electrical energy between the components, obviously. So they're rated to handle the high DC voltages that the solar panels put out, unless of course you're using individual inverters. And they require proper insulation and protection against UV exposure. So what you'd normally do is you would either put the cables behind the panels, or you would run them in conduit until you can get them inside the roof into the attic space. So yeah, you got if you don't have microinverters, you've got the DC isolators, and then you've got the AC isolator, which disconnects the AC side, usually between the inverter and the DB. Unless of course you're using microinverters, in which case you have a AC isolator per array, because some jobs you'll have, I think the biggest one we did, there was 12 different arrays on the building, so we had to have 12 different isolators before it went down to the switchboard. And some will have a battery storage. This isn't always the case, but some systems store excess energy generated by the solar panels for periods of low sunlight or power outages. They're often lithium-ion batteries for efficiency and longevity. They provide backup power and increased energy independence. Some examples are like the Tesla Powerwall, which store a bunch of energy. Yep. However, just go. All good. If you have to go now, go now. The YouTube channel is called Tutor Stew, capital T with a capital S and no space in between. And I should have the video up within half an hour of this session ending. Cool, and then earthing. So a safety system that connects exposed metal parts to the earth, to the solar installation to ground to prevent electric shock. So each panel gets its own earth connector, and depending on the design of the system, sometimes you'll run an independent earth up to the system, to the panels itself. And then depending on the network, you'll either store it in battery and keep it, or you can export it. It depends on the local network and the local regulations. Thanks, Cody. Cool. So DC acts very differently to AC. So as the current is continuous, a continuous flow from positive to negative, or AC is constantly changing from positive flow to zero to a negative flow back to zero and repeat. This leaves us with one significant hazard because DC constantly flows in one direction and does not change in magnitude and pass through zero like AC does. It will continue to flow in a much more sustained way, even in places it is not supposed to, like air. At high enough voltages, DC will continue to flow through the air if a path is provided. This is called arcing and causes significant damage when allowed to happen for prolonged periods of time. The arcing causes heat, burning, and in the right conditions, fire. This is also the case with high voltage AC, but because AC alternates, we're more likely to be able to break the current path rather than DC. Sorry, it's a YouTube link, so it's going to play an ad. I'm sorry. So this is just a comparison between AC versus DC, using a switch, a 220 volt supply, and three or four bar heaters. So you notice the switch opens, but there's a very small arc. You have to watch closely to see it. So you notice how quickly those bar heaters heat up because it's DC, and the arc, when the arc is going, those heated elements continue to stay heated. So yeah, those are the dangers of DC switching. So yeah, so it's continuous power generation. So some of the hazards are the fact that it's continuous power generation from PV panels. So the PV panels generate electricity whenever they are exposed to sunlight, even if disconnected from the grid. So there have been instances where people have been handling solar panels, they've accidentally touched one of the ends of the cables that come off it, and it gives them a zap. So there's no off switch for the panels themselves, which means live DC voltage is always present during the day. The only way to turn it off really is to cover the panels completely with blackout material, or work at night, which is another risk in itself. So maintenance or emergency shutdowns can be dangerous without the proper precautions like covering the panels. Accidental contact with live DC circuits can lead to severe electric shock or burns. And then you've got the battery storage risks. So high DC voltage stored in batteries poses a risk of shock during installation or even maintenance. When you do UPS battery installs, most of the time the batteries come slightly charged or even sometimes fully charged. And so when you're working on those UPS batteries, especially if they're just the big lead acid batteries, it does pose a risk. And which is why if I do big UPS jobs, it's better to get the UPS company to come and install them. So yeah, fire, overcharging, physical damage, or short circuits can cause thermal runaway, leading to fires. Has anyone seen a lithium-ion battery fire in person? Was it like a tall battery? Yeah, that's all I've seen is a phone. Okay. Was it a Samsung? I don't know if you guys remember, there was the Samsung Galaxy Note a few years ago. Yeah, it was. I'm hoping it was a Note, where they weren't even letting them on airplanes because they had a habit of just catching fire spontaneously. The one I saw was a Ryobi battery, so an 18-volt Ryobi battery, which a guy had on site. I don't know why, but he left it near a grinder. Someone was grinding, and the sparks from the grinder somehow landed on the battery in the right spot, melted through it, and the battery caught on fire. And you just really can't put them out. So we just kicked it into a drain hole, a concrete drain hole, and just left it to burn itself out because there's nothing else you could do about it. Yeah, so batteries store significant energy and they require proper handling and safety systems such as cooling and ventilation to prevent accidents. Lithium ion batteries commonly used are particularly sensitive to overcharging or damage, so it's usually preferable to put them outside if possible or places that aren't going to be exposed to extreme heat. Or in the case of a UPS battery system, they normally put a air conditioning unit, usually two. So one as backup on separate phases as well. And they normally, to cool the room. Cool. So poor installation practices, hazards. So you got cable management issues. So poorly secured cables can lead to insulation wearing, arcing, or shorts. And incorrect cable size can result in overheating or voltage drops. And earth leakage. So obviously with DC, you've got the chance of leakage to earth or the frame of the. So worst case scenario, your earthing's not connected properly, and you get a leak to the frame, which then leaks to the. Normally, you would install the solar panels with rubber feet underneath the brackets. Sometimes they don't, so it's screwed directly into a tin roof. Now all of a sudden your tin roof is live. So, and then anything touching your tin roof might become live, like your worst case scenario, your satellite dish and your satellite dish cable, and then that might then fry your sky or whatever's plugged into your satellite dish cable. So you can see how if something's not installed properly, it can have a flow-on effect and damage quite a few things. So, yep, so exposed metal parts of the system, if not earth, can become live and dangerous. So proper installation practices ensure safety and system efficiency. And there's actually a standard AS/NZS 5033 that the requirements for cable routing, earthing, and protective devices to minimize risk. There is also a legislation or best practice guide for solar installs as well. Cool. So that's all the material we have to cover over tonight. Because you guys are already in study setup mode, I would recommend you guys do some work on your online stuff on the Learning Hive, just to get it all ready to go. And right now I am